Here we are talking about probabilistic risk assessment, and for probabilistic risk assessment we have to understand probabilistic modeling. Of course, through simulator and its examples and discussion, we understood what goes into building a defense in depth into a plant. Now we will see the probabilistic modeling. This is lecture number 3 of week 5. So, what we will be discussing here is role of probability and reliability engineering. Because it provides, in simple words, it provides fundamental for probabilistic risk assessment. And then PRA, again, it finds its application on risk simulation, either in the form of a risk monitor, or as part of a human factor in risk simulation in the simulator environment. Then we will be discussing data requirement. As I had mentioned, data requirement is critical to any study, and same thing applies to PRA also, because a quality of data only can produce good results. And then it becomes all the more important in respect of human factor, because 50% efforts it goes into collecting data, including human factor data, and human factor data has got a higher uncertainty. So there is opportunity available on the simulator to reduce this, or rather to integrate the plant specific data on human performance with the simulator experience, and to reduce the uncertainty in the data. And then probability and reliability, how it is required to study probability fundamental, general, and especially distribution, because distribution are basically there to show the data trend, and unless until we map them on a distribution, our data applicability will be very weak. So probability distribution will be of course, whatever the discussion will be there, only whatever we use in PRA to the extent possible, and others distribution can be studied in open literature. So now before if I go to the probability distribution, I have to understand what is my plant. Plant can be divided into two parts: process system, so that means process system data, and safety system or safety support system. Okay, so these are the two major category in the plant, and these two, they build the process systems are required for ensuring reliable operation of the plant, and safety systems are required for a timely action, so that and that too without human intervention, because safety cannot be compromised. So automatic actions are taken, and later on human actions are expected to ensure through diagnostics if any corrective actions are to be taken. The reliability estimates data, they come from the plant based on the performance record. Let's say, for example, I'll give you some very simplistic and very primitive aspects about the failure data, because failure data are the building block of any probabilistic study. So let us say I want to understand my pump performance, okay, in terms of reliability estimate. So there is a parameter called failure rate, and it is the notation is lambda. It is expected lambda. So I'll say lambda pump, P, that is pump failure rate. How I'll derive this information? Total number of failure and the period of data collection. Okay, so what I have here is total number of failure are 5. Okay, and then accumulated time is nothing but there were 3 pumps, 10 years period, and 8760 hours are there in 1 year. So I'll get estimate of pump failure 1.9 into 10 to the minus 5. Don't you think it is a very valuable estimate that you have obtained? And if you are talking about maintenance failure or mission time to failure, then let's suppose if I want this pump's probability of failure for next 10 hours operation, this is failure per hour. So I'll simply multiply by 10 and I'll get the failure. So these are some primitive techniques that are available, and they are very useful. Advanced techniques, they come later on, Markov model, Bayesian updating and all, but we should know these primitive techniques which are basically solving our purpose for a major part of our risk assessment. Okay. Okay. Now that was there for safety system, that is failure rate per hour per unit time is for process system, continuously operating systems. Now for a standby system like my power supply, diesel generators, okay, for my shutdown system, they will get activated only when there is a deviation in the plant from normal operation, and the plant has to be brought to the shutdown state. So they will get activated. So that is where the role of safety system comes into the picture. Okay. So so standby system. Now standby system will come only when demand is placed. Okay. So that means demand failure probability. Okay. So the demand, let's say for example, I have 10 years of data. Okay. And I have again the 3 pumps or 3 diesel generators. Now earlier it was for pump, now it is for diesel generator is a emergency power supply standby system actually. So 3 diesel generator and then 250. There were 250 demands. And 5 failures were noted there. So 5.6 into 10 to the minus 3. So this is a demand failure probability for now. In the fault tree, we can straight away estimate this, but then diesel generator starts and operate also. So if suppose we expect that the power failure loss, historical record shows that it was their mission time was let us say 2 hours. Okay. So we can failure rate what we obtained and into mission time. Let's say we assume that failure rate is 5 into 10 to the minus 3 into 2. So we will get the failure probability unavailability. Okay. So the mission time probability operational unavailability can be given as, so we got QT also, we got U also, and if I add these two, I will get total unavailability. Okay. So let us see. I have added here 5.6 into 1 to 10 to the minus 2, and I got a overall unavailability. You saw demand failure probability was less, and this is higher, and this is, so net effect is this is dominating here. Okay. Now once I have obtained this data, I can plug into my fault tree or event tree for creating a PRA model. So that means in short, you got to know how the probability estimates are developed for a continuously operating system and for that is a process system and standby system, and these two are very vital things. The above slides also shown primitive and effective strategy. Okay. Later on a lot of complexity will come, but then if you through these lectures and all, if you pick up this one, this is the minimal, and you will be able to develop a model of the plant. Now you will say there were 3 diesel generators and failure probability is this one, the common cause failure will come to picture. But those things are later on. Let us start one by one, step forward. Okay. Now we all along in our previous slides we had assumed a exponential distribution. Exponential distribution means failure rates are constant. We'll discuss about that. It's a very simple distribution. We use lambda, and then finally we assume that the failure rate will be constant only, and we give it. And in actual practice also, let me assure you, we use in PRA modeling mostly the exponential distribution and Weibull distribution. Weibull distribution we use for lifetime data estimates, and then exponential distribution or log normal distribution. These are some 4-5 distribution we use, and if any situation comes, then we use those data. So now probability distributions are concerned, like we have process systems. So process system means continuously operating system. So continuous distribution is one thing. Continuous data means it can occupy a continuum of values. Compare it with the discrete data. You will understand better. Discrete data means number of diesel generator failure 5, 2, 3, 1. There will not be any fraction. But in continuous distribution, 1.5 hours, 1.8 hours. So this will be continuum of data is the domain, and here it is the discrete data. So there are two types of distribution we have: continuous distribution and discrete distribution. Continuous data are expressed per unit of time, and discrete data, they are expressed in terms of per demand, or in terms of probability, or in terms of availability. Okay, and I showed you in previous slide how you get per demand data, how you get unavailability data, and finally you can call it unavailability, system unavailability. Okay, so now let us see. Now given a situation that you have data, but you do not know which distribution you should use. I mean, you should be very sure which distribution or which trend in the data, and that it is following. So simplest technique is probability plotting. Probability plotting means there is a exponential graph that is available. Similarly, there is a Weibull graph available, there is a log normal. There is some special advantage with Weibull, I will come to that. If I plot data on a probability paper, exponential probability paper, and my data somewhere it is coming like this. So this line is passing through this, and later on we have to perform regression analysis also, but then I am sure that my data is following exponential distribution. Okay. Now second, if I have a Weibull graph, in Weibull graph, if I get this, and if the angle of this this is called shape parameter, if this is a beta factor, if it is 1, then again it is exponential distribution. If it is 3 or 4, then it is a Weibull. The trend shows failure rate trend actually. So Weibull distribution is also called as universal distribution. From here we can make out which distribution my data is following. So people, it is useful for live testing experiments and all that. In reliability there is a special laboratories which put the component under the stressful condition. Those stresses could be temperature, humidity, it could be corrosive condition, and the component performance is monitored from outside of the chamber. So, and then it's not only one component, there are some couple of components are placed in service, and their failure or their degradation will tell us the reliability of those components. Now I told you about this, I don't know whether I have discussed it. Now I got this data, but this is, I am seeing it. But if I have to say how perfectly mathematically or in a demonstrated way I have to tell that it is exponential distribution, there is something called regression analysis, and if coefficient of correlation is 0.9 or more than 0.9 or somewhere, now it depends on the people who are in the decision making, but if it is 0.9, then that means it is following an exponential distribution. Okay. So regression analysis forms you can see anywhere in open domain. This regression analysis is available, or will later on somewhere I will show you. I have a data and I have plotted it on a graph, and then finally I am trying to give the coefficient of correlation, and if that is 0.9, that means the data at the line represents the data. Okay. Okay. So probability paper we have seen, Weibull distribution also we have seen. This is a log normal distribution, and this distribution, so 1, 2 and 3. These 3 distributions are used extensively in reliability engineering. If beta factor is 1, as I mentioned, if beta factor is 1, this is a exponential distribution. If 3 or 4, log normal or log normal distribution, we get an indication. So it is better to keep a log normal probability paper and plot the data on that one and see and so here beta is the slope parameter or shape parameter, and there is something called alpha at the this axis, and that is called characteristic life of the component. So you can see the characteristic life here and the for the component. Okay. So data analysis. Now we have done the data analysis. So we said that we use exponential distribution because this is a constant failure rate period, with the time. But here which distribution will apply, and when it has come at the crossing level where exponential distribution should be used. So this is called the life cycle curve, or it is also called popularly bathtub curve. So what is this parameter? It is called probability density function. Okay, and this is the time. So here some component, why this shape? Some component have early failure. If I put something like, and how this curve has been created, some n number of components were put to test. So initial failure will be highest, then it will reduce and it will come to this situation, and finally it will be constant. That means let us say 1 failure per 15 hours, so that will continue over here, and then finally it will increase. Why? Because of aging period. So this is called useful period, this is called early failure, and what early failure reflects? Early failure reflects quality related component or learning factor or any design deficiency which are there, they will be reflecting. And constant failure rate is basically, now we have all removed the weakness in the component, and now we are having a constant failure rate. But then and here there is a maintenance. So what we do is maintenance. So in maintenance, when the failure rate increases, we again do the maintenance, we bring it down. So like that we perform continuous maintenance and bring it down. So the mean curve comes like this. So maintenance plays a very important role in keeping this as a horizontal line, because the moment component will degrade with operation, but it is brought back to and you can do it. But after some time, what will happen is, if the failure rates are going up, you cannot bring them down, and then finally it will go up. So what has happened? The inherent aging period has started here. Now, so extensive aging management program is taken up to address this situation. And once we do aging management program, then again our curve will come like this, and then our normal life, and may not be here, so it will become somewhere here, but it will be coming down drastically after incorporating the aging. What we will do is, we will replace the component which have gone beyond repair, we will replace them. Some component we will do permanent extensive overhaul, and some new component will be installed. So repair, replacement and modification, and finally we'll come back. This doesn't happen at component level, it happens at the plant level also. Only difference is, there the plant unavailability is very high initially, then comes down constant, and again it increases. So at plant level, the bar chart will look something different. Okay, but this is a very important insight, that again that is also bathtub curve. It is developed in terms of unavailability. Okay, now what are the distribution probability density function? The probability density function is instantaneous, based on instantaneous failures. It is developed. That means what will be as a function of time, continuum of time, what will be the failure rate? Okay, so mathematical expression for FT is nothing but probability density function, PDF. Okay, and this is called cumulative density function. Cumulative density function, it is mentioned here. Okay, what happens is, all these failure phenomena, if they are added, they will build a constant curve, and here it will be, they will be reaching 1. Okay, because all the failures are represented, and then if I have normal distribution, this is a normal distribution. So mu is the mean time, it is represented mean value. If it is a log normal distribution, the distribution, I will come to that, it will be a median value. So, but you have to remember two parameters. One is cumulative density function, wherein all the probabilities go on adding and they build up and go to 1. Probability of failure is not more than 1. It is 0 and 0 to 1 is the range for probability of failure. Okay. So, we have this normal distribution. Now, how our failure density PDF is characterized? Ft is equal to, for exponential distribution, lambda, that is failure rate, into exponential of minus lambda t. This is the PDF of exponential distribution. Okay. And if I have to get the Ft, that is cumulative density function, then I have to integrate it 0 to t. Okay. And then finally I will get all the failure rates, and I will get this is equal to based on the time. Okay. What is value, and finally all the things added up, it will become 1. So, from here we derive the reliability is nothing but 1 minus failure probability. Either a component, whatever is the reliability, the failure will define failure probability. So, 1 minus failure probability. So, by this we come to an expression of reliability. If you want to see the derivation of reliability based on the first principle, probably you have to refer my presentation on as part of risk-based engineering, and there also it has been explained in probability density function. Okay. So, reliability, please remember this term as a risk assessment person, that reliability is nothing but exponential of minus lambda t, and failure probability is 1 minus lambda xt. So, what happens? Exponential distribution is a one parameter distribution, and that is lambda. Okay. This is what we understood from this slide. Okay. Now, we see some other, so I have not discussed other distribution in detail, but then we have got 3 discrete distribution. Discrete distribution means how many number of buses will, now 1.5 bus will not come, it will be numbers. So, it is a discrete distribution. How many components will fail, or how many, so how many, when it is a number, then it is a discrete distribution. So, we have uniform distribution. Probability of each event is same. Simple example, we are rolling a die. So, probability of number 1 to 6 is 1. Okay. Initially you go on collecting data, when you theoretically, if you can do infinite experiments, you will find that probability of each number is 1, same xi, So, then binomial distribution, R out of n. R out of n means probability of R out of n is equal to NCR, that is combination, permutation combination, NCR is nothing but probability of individual component performance raised to power R, let's say probability of failure. So, probability of number of failure minus into 1 minus P, okay, and n minus R. Okay. So, what is P? P is nothing but, let us say we had 6 pumps in line, and out of 6 pumps, if 2 pump fails, system failure occurs. So, n is 6, n is 6, okay, and 2 R, and then if we what is P? P is that, on pump failure we have collected data, and you found that probability of this pump failure is let us say 2 out of 1000. So, 2 into 10 to the power minus 3. So, this will be P. So, this is individual component characteristic, and that is how. So, if I have redundancy into the system, okay, and how to estimate the, so this binomial distribution is a very elegant mechanism, model which provides a way to characterize the failure probability of combination of component. Okay. Poisson distribution, probability of occurrence of event, number of buses coming to a bus stop and all that. So, this number n is equal, n is a random number, and then small n is the number it is occupying actually. So, this is what we have, and then we have to discuss Weibull distribution. It is a continuous distribution. You can see here PDF of Weibull distribution is given as beta t raised to power beta minus 1 alpha raised to beta. Beta is slope, a shape parameter, alpha is the characteristic life of the system, and then exponential minus t. T is the period against which we are trying to obtain the PDF, and alpha raised to power beta. So this is a very useful distribution. Beta is a slope or this thing parameter. So slope, if the line slope is 1, then we get, and alpha is the characteristic life. So exponential distribution and all. Now continuous distribution. Continuous distribution is nothing but we have exponential. You saw exponential is PDF is equal to lambda x minus lambda t. So this distribution looks like this actually, and its cumulative will be of course FT, CDF, PDF. Similarly, log normal distribution. Log normal is basically a skewed distribution, though it has been shown here. It is a skewed, it comes like this and it goes like this actually, you know. So and then finally it's a standard. So this is a normal distribution, two parameter sigma and mu and sigma are the two parameter. Like this was a single parameter distribution, this is a two parameter distribution. Applications are in design, variation in the component thickness, current, any voltage, how they will vary, and PDF is defined by 1 upon sigma into 2 pi, exponential minus 1 by 2 t minus mu upon sigma whole square actually. So this is very complicated. Now you tell me if I have to get an FTA, it is a very complicated thing. So what I have to do? I have to convert this probability distribution, that is normal distribution. Normal distribution is nothing but bell-shaped distribution, both sides equally distributed, you know. So though this line should have been little here for getting the mean of the distribution. And then standardization, what we do, we develop another parameter, Z parameter. So that is nothing but t, whatever t has been given, minus mu upon sigma, and then the mean becomes 0, and it has got again like normal distribution, it is a spread of Z minus side and plus side. So this is what is log normal distribution. Log normal distribution is when a parameter's logarithm is taken, and then logarithm will give you the normal distribution. That is what the log normal distribution is there. Okay. So and then log normal distribution is here. So okay. So this is normal distribution, and for log normal, as I said, FT dash is nothing but len of t, original parameter, and then we have sigma t, that is standard deviation 2 pi exponential minus 2 t dash again and mu t divided by sigma t, that means standard deviation of the log normal distribution. Okay. So and we have got the distribution over here. Here is the median value, not mean. It is the median value of log normal distribution. I told you when data comes from different sources, independent sources and from generic sources, then we use log normal distribution, and it is defined as the error factor. I will discuss that thing. Error factor is nothing but 95% bound here. So median value 95% down divided by median value. We will come to that actually. Okay. Here I have not shown this one, but again, as we said, normal distribution, it will have a cumulative this thing. Okay. Probability approach are, so now we have understood the fundamentals, and it is very important to understand the probability distribution. Without that, we may not be able to do justice to whatever development work that we are doing. So in this lecture we have discussed probability distribution, and the next we have created the background for probabilistic risk assessment. So in next lecture we will take probabilistic risk assessment.